Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandria, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on our access to the outer solar system. And after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe study and for information on future webinars, please visit the Interstellar Probe study website. And now I'd like to introduce today's speakers. Michael Paul is a program manager at the Johns Hopkins University Applied Physics Laboratory. He has held many prestigious leadership positions in both commercial and UARC institutions within the space industry. Michael is currently the program manager of the Lunar Surface Innovation Initiative at APL and is the program manager of the Interstellar Probe study at APL. Robert Stough is the payload utilization manager for NASA's Space Launch System rocket at NASA's Marshall Space Flight Center. He is a recipient of NASA's Exceptional Engineering Achievement Award, and he is here today to discuss the progress the SLS program continues to make. And now for the presentations. Michael, the virtual floor is yours.
Thank you, James. If you could go to the next slide, please. Oh, I'm sorry. This one. Thank you. Thank you also to everybody who's joined us today. So some of you have seen these episodes in the past, the series that we've been running to share what we're doing with this study for Interstellar Probe. And so you've heard about the background about what we're doing and why. Now, for those of you who are joining us for the first time, I encourage you to go to interstellarprobe.jhu.edu and find our recordings of past shows. You'll find information on the big picture in our first episode. Why are we doing this study now? And why is it time to do a mission like Interstellar Probe? How we're going about the study, but also how we're going about crafting a mission concept that can be executed in the near term, in the decade 2023 to 2033. And you'll find discussions about the key explorations that we're considering. What is the science that we could capture with a mission like this? You see here the image of the graphic that you see behind me as well of a notional, what does our star look like from the outside? The sun is there in the center. The edge of the sphere that you see there represents the boundary between the solar wind, the bubble that we live in, and the outer solar and the outer galaxy, the interstellar medium that we're all living inside of. You see also in this graphic, you see a number of actual pictures of actual stars and their heliospheres. The heliosphere that isn't a photograph, isn't a picture in this graphic here, is ours. We don't know what our star system, and our habitable astrosphere, we don't know what they look like from the outside. And we do not understand what the full dynamics, boundary, and outer conditions are, because we've only had images and science data that look out from the inside, and that can lead to ambiguous results. And Voyager, which is still flying, Voyager 1 and Voyager 2, through this boundary and out into the interstellar medium. And so this study is crafting a mission that can be executed soon, relatively speaking, to make an exploration that has never been done before. Yes, Voyager is out there, but the instruments and the planning and the timing of this mission are unique. Also in the previous webinars, you'll find some very detailed discussions. If you could go to the next slide, please. Thank you. Of what that science is, how we will measure, and what we want to learn about the transit between here and the edge of the solar system, what we want to learn traveling through that turbulent boundary region where the solar wind meets the galactic wind. And then what happens to the environment once we leave our solar system and actually get outside of that habitable bubble that we're all inside of and get into the pristine, undisturbed interstellar medium. How far out that extends, we don't actually know yet. And so these are the things that this study is including in the science. Future webinar episodes are going to detail the spacecraft, the mission architecture, have more information on the science, and help you understand what we've learned and what we're considering as we move forward over the next 2 years and complete this study. So we're focusing on how to accomplish this exploration of the heliosphere in the near term. You will find the phrase pragmatic used frequently. And what we mean by pragmatic is that we want to craft a mission concept that can be executed without waiting for breakthroughs that are indeterminate, unexpected, perhaps planned and foreseen by technologists, but not necessarily something that we could bank a mission on and say, we'll get this job done provided that such and such a breakthrough occurs. We are only considering technologies in this study that have a reasonable chance, a reasonably low risk chance of being ready for the launch pad by 2030. To give you an idea of what the scale of the mission is after launch, somewhere in the 2030 plus timeframe, we want to get to that outer boundary of the heliosphere in about a decade. So out to 70, 80, 90 AU and begin measurements of that turbulent region about a decade after launch. How do we do it? That's why we're here today. We're really pleased to have Rob Stough from the SLS team join us. They've been working with us for over 2 years now, trying to help us understand what SLS could do for a mission to enable reaching that boundary of the solar system that fast. To give you an idea of what's been done before, Parker Solar Probe was the highest energy launch in history at 152 plus kilometers squared per second squared. Parker had the highest launch energy. And you all have at least the beginning of an understanding, if not an in-depth understanding. Mass and velocity, they contribute to energy. So we're gonna, with this mission, have a similarly low mass spacecraft, but the launch energy that SLS can provide is more than twice what Parker was able to achieve, more than twice of what New Horizons achieved. And so the capability that SLS brings to the table is profound and enables this mission to do what we're asking it to do. So you're gonna hear a lot from Rob. If you could go to the next slide, please. We're going to hear a lot from Rob about the performance of the system itself, but I want you to realize also that exciting science about this shield, this bubble, this boundary that we have between our home and the outer reaches of the galaxy, if you will, that there's other science that can come along with it. Flybys of Kuiper belt objects, looking back and understanding our dust disk, which we again can't see unambiguously from our vantage point inside of it. And even a view to the outer, to the early formation of stars and galaxies that is shrouded by that very same dust. The science opportunities that this mission brings go even beyond the high priority science for heliophysics that are the core and the reason to be for this mission. Next slide, please. Just as a teaser, I want to share with you just a little bit of an idea of what the mission architecture looks like. An Earth, Jupiter, Saturn sequence, for example, that we have identified with a few different launch dates here, can enable a very, very high speed escape from the solar system. And this is going to be, this is just a snapshot from the middle of a study that we have begun. And we'll have a lot more on that in August and in September with a report coming out in the fall. And with that, I want to turn it over to Rob. And thank you, Rob, for joining us again today to talk about SLS, where it is and what it can do for Interstellar Probe and for other missions that have a desire to head out to the far reaches of the solar system.
Thank you, Michael. And it's an honor to be here to talk about SLS, and I'm so happy that it is such a game changer for the Interstellar Probe. And I'll get into the reasons why a little bit later. The SLS is the Space Launch System. It is a very large rocket. It looks a lot like shuttle. It uses some shuttle hardware, but it's very much a different animal entirely. It's a new rocket. So next slide, please, James. The SLS is a vehicle that's planned to have an evolutionary path to it. It is planned to evolve from the Block 1, which is the configuration on the left. The Block 1 will have both a crew and a cargo configuration. It will fly the boosters, a 5-segment set of boosters that are new development. They produce a lot more thrust than what were produced during the shuttle program. It produces about 1.4 ton or 1.4 million pounds of thrust per booster. And then our core stage, which is the large orange thing in the middle there, it has 4 RS-25s. RS-25s are the space shuttle main engines that are reused for this program. We have 16 of them, so we have 4 per flight, 4 per core stage. So we have 4 flights of our heritage engines that flew on shuttle that we can use. Likewise with the boosters, that we have enough for 16 sets or 8 flights, or so 16 boosters, 8 flights total of steel cases that you see there. So, but I should also mention the RS-25s, they produce about 500,000 pounds of thrust. So the core stage alone produces 2 million pounds of thrust. If you add it up, you're upward of 8 million pounds of thrust, almost 9 million pounds of thrust. So it's a very capable vehicle. So moving forward through our evolvability path here, our next configuration is the Block 1B. It also will have a crew and cargo capability. What makes them different is that the Block 1 has a delta cryogenic second stage. We procured a stage rather than built a new one for that vehicle. It was hard to be able to develop both the exploration upper stage and the core at the same time. So we chose that as an intermediate step, but what we're aiming for in terms of design of the vehicle is really the Block 1B, Block 2 capability, which includes the exploration upper stage. The exploration upper stage has 4 times the propellant, and it's a very capable stage. Overall, we target about 40 tons to the moon of cargo delivered to the moon for the Block 1B vehicle. And then stepping through to our Block 2 configuration, at some point we're going to run out of our boosters and we'll need something to replace them. So we have something called the BOLE, Booster Obsolescence Life Extension boosters, that will come into play. And at that point, we'll have greater than 46 tons of capability that we can take to the moon. That's metric tons, not English tons. So with that, let's get into where we are as a program. Next slide, please. Is the rocket real? Next slide, please. And so before I get into the progress that we're making on our inaugural flight of the SLS for Block 1, let me talk a little bit about the components. I talked about the boosters already, the RS-25s and the core. One thing that you'll see, it looks a little bit like the space shuttle, and you think that, oh, well, we're not very innovative in that respect. Well, this is a whole new vehicle. This is a whole new design. The core stage, there's very little left over from the shuttle in terms of the tooling and everything to build the core stage. Although we did stick to the 8.4 meter diameter tanks. The external tank for shuttle was also the same diameter. But what was really innovative about shuttle, and it's something that actually followed through into SLS, is the fact that the structural design. What you don't really realize when the vehicle's sitting on the pad, and I'm going to point to my little picture here behind me, the whole weight of the vehicle is not directed through the bottom part of the core stage. It's actually directed through the boosters. The vehicle is actually setting on the boosters, and there's a load path that goes through the inner tank. So you can sort of look at the core stage in the middle there. There's a little section in the middle that's called the inner tank. That's where the loads are transferred over to the boosters. And what that allows you to do is lighten up the LH2 tank, the hydrogen tank, which tends to be very large because of the density of that liquid propellant. And that allows you to save quite a bit of mass doing that. So it is an innovative approach, and it helps us quite a bit on this program, on this rocket. Next slide. Oh, and I should mention from the previous slide, all of our hardware is developed. It is built and completed. We are going through our final tests right now. So that's why you see green marks across the board. And I'll get into that a little bit more later. So next slide, please. Thank you. And so there's a video here, James, if you want to play it. This is showing that we are starting to stack our boosters down at Kennedy Space Center. We had our boosters poured and ready to go in storage out of Utah. They finally made the journey all the way from Utah, Promontory, Utah, to Kennedy Space Center, and they are now currently preparing them for stacking. The picture on the right here, you can see how the aft segment is actually being mated to the aft skirt and nozzle. And so this is a very exciting time, and really shows you a commitment to flight. Once you start stacking the boosters, there's no going back. You can't put everything into storage. You have to fly. So it's a very exciting time. Next slide, please. So here's a video of our core stage green run. What you see in front of you is the test stand, the B2 test stand at Stennis Space Center. The core stage is being lifted and being placed into that stand for our green run test. What the green run test is a series of tests that allows us to put the core stage through its rigors, make sure that the avionics work, that the propulsion system works properly, that there's no bad leaks anywhere. LH2 is a very difficult propellant to manage. It is one of the most fundamental elements, and thus it will leak. It's just a matter of how much. And so we need to make sure we test everything thoroughly. And this test really represents an acceptance test for the stage. Before the end of this test, the stage is actually owned by Boeing. And after the test is completed and everything is good, it makes its transition over to ownership by the government. And so from here, we will take it down to Kennedy and actually stack it with the rest of the vehicle and launch. So it's a very exciting time. There's 2 critical tests that have been completed so far. There was a modal test initially back in January, and just recently they had a power on test of the avionics. Both those tests passed with flying colors. And the next test, I believe, will be flowing propellants, and then they'll test TDC and then actually do a full burn of that stage in the test stand. Next slide, please. So just so you know, the rest of the vehicle's ready. Our cryogenic upper stage, the interim cryogenic propulsion stage, all the way to the left there is ready to go. It's actually a Delta, has Delta heritage. It's a Delta cryogenic second stage that we've repurposed for SLS. It is modified. It's not exactly what you would expect to see from a Delta, but it's very close. Our adapters are also ready, our LVSA, which is in the middle, and also our Orion spacecraft adapter on the right, which includes our secondary brackets, secondary payload brackets there. And that will help, that will be the interface, if you will, between us and Orion. Next slide, please. Here are some really nice videos of our structural testing. We finally completed our structural testing of the core stage and all of its components, which include the engine section, inner tank, but also more importantly, our LOX and hydrogen tank. The one on the left here, James, if you want to click on the video there, this is a video of our test to failure of this tank. And one thing you should know is that it was very successful. And here was the initial failure where the tank popped a little bit and the pressure started leaking. And we didn't really expect what happened next. We thought that it would just, the pressure would go out and that would be it. But that's not what happened. Actually, this failure was a very dramatic failure. It was a successful failure. You want to pause that? Thank you. It was a successful failure. What we found through this test is what the limit of the design could take us to, and that was a factor of safety of 2.6. It was well over designed. We were very happy with the test, the overall results. It showed that we have plenty of margin in that tank. If you want to play the video on the right, please. This one doesn't have audio, but it shows a test of failure of our LOX tank, which is above the hydrogen tank in the core stage. And this one was surprisingly right on the money. After we ran this test, we found that the factor of safety was right on 1.4 for the tank, what we designed for human spaceflight. And another thing to mention, you know, I showed the evolvability path. We build our hardware to make sure that we can survive each of those vehicle configurations. The hydrogen tank is really driven by Block 1 loads, and so when we say that it's built for all the configuration, that is more influenced by that design. But a lot of the other components, like the LOX tank, is really driven by the BOLE loads or the Block 2 loads that will come on later in the overall manifest or flight evolution, if you want to call it that. So, all right, let's move on to the next slide, please. Okay, so what progress are we making for future flights? Aren't we already talked about Artemis 1 and all the hardware? Well, this is the hardware for our follow-on flight. Our OSA is in the process of being welded. Our core stage piece parts are for the most part done. We have I say that loosely, the primary structure is done. We have to put all the bits and pieces together. So the forward skirt, the inner tank, and the liquid oxygen and hydrogen tank are done. All the booster segments have been poured and have been ready for Artemis 2 for a while. In fact, we're pouring them right now for Artemis 3. The RS-25s are the test campaign behind them for the second set is complete. In fact, they're used as line replacement units for the first flight. So that's our plan, is to have a set ready just in case we have to swap them out. And then our diaphragm for the OSA on the lower right is ready to go. Next slide, please. The third flight for Block 1B and Block 2 are RL-10s. I mentioned our exploration upper stage. Well, it uses 4 RL-10s. We have procured a whole set of them, and we're going to use them for both the ICPS and the exploration upper stage, but we have 5 ready to go. We did a subscale test of our Bulle booster, which is the big Block 2 booster. So that was a successful test that tested the propellant, and I think also the insulation. Our universal stage adapter, we have completed a manufacturing demonstration. We have an inner mold line tool, which you see there underneath the panel, and the panel above is a quarter of the overall universal stage adapter that will mate the Block 1B exploration upper stage to Orion. And then it also will hold payload as well, co-manifested payload for lunar transit. And we made a lot of progress on our RS-25. We're starting to manufacture them for the first time in 16 years, which is really amazing. And we're also incorporating a lot of new manufacturing techniques like additive manufacturing to bring the cost down of that engine. Next slide, please. And let's talk about how this rocket becomes interstellar. And let's get into the Block 1B configuration. Next slide. The Block 1B configuration, like I said, has the exploration upper stage, which has 4 RL-10s, has an inner stage to mate the core to the exploration inner stage. I'm sorry, the core to the exploration upper stage. And then we have a payload adapter on top, which we have tooling at Marshall Space Flight Center to build that payload adapter. And we're planning on, for this study, to actually adapt that hardware to build adapters for the Interstellar Probe to 4 additional stages. And I'll get into that a little bit. And all of that I'm going to talk about is going to use this configuration flying payloads and stages underneath our fairing. And our fairing, we have a fairly detailed government design, and we're on the verge of committing to a committing to procurement, essentially going out on procurement for that item. Next slide, please. All right, let's talk about, so for this study, we were talking about flying in the late 2020s. The obvious vehicle configuration of choice is the Block 2. Just to give you an idea of how things will progress from Block 1B to Block 2, the initial configuration will use Heritage boosters. Well, booster segments, we'll still have the 5-segment booster. And then we'll have our Heritage RS-25s reused from the shuttle program. Then after that point, we'll transition to our new production engines, which I mentioned we're starting already. One thing that's different about these engines, the original rated power level of that engine, it's been upgraded over the years through the shuttle program. And for the initial flights of SLS, we're going to run them at 109%. And then we'll transition to 111% on the new production engines. The reason why we can't go up earlier, the engine design is overall, for the most part, is very robust, and we understand that engine in and out. There's plenty of test data going up to 113%. And so, but the way the contracts are written and the way, it's mainly how the contracts are written. We are not allowed to go much higher than that, to 111% on our initial builds, essentially. And then after that point, we will replace our boosters with enhanced performance boosters, the Bulle boosters, which are composite cases instead of our steel cases. Still a 5-segment booster. What's also different is we're using a more energetic propellant. So the thrust goes from 3.5 million pounds to 4 million pounds per booster. So we get very close to getting to 10 million pounds of thrust for the overall vehicle when we get to Block 2. It's very impressive. Let me talk about performance a little bit. When I quote performance for the Interstellar Probe, the performance is generally conservative. We use mass growth allowance on all of our mass estimates, and we have mass manufacturing variation. It's a 3 sigma high on variation oftentimes. We use nominal performance on the RS-25s and the RL-10s, which those engines, the performance is fairly well understood, and there's not a whole lot of variability there. So not a big risk there. And then for our boosters, we use lower performing boosters. Since we're using solid rocket boosters or solid rocket motors for all 3 configurations, they are sensitive to temperature, and that's inherent to solid rocket motors. We generally just use what we call propellant mean bulk temperatures equivalent to that of February, so that we stay fairly conservative, and it bounds pretty much the entire year in terms of performance. And also we hold back manager's reserve. So the overall takeaway here is that we're going to upgrade the vehicle performance will go up as we evolve, and that we are very conservative on our performance. So next slide. Recent developments, we have recently redesigned our EUS to our exploration upper stage to be optimized for the moon. Actually, the overall vehicle is designed to get as much performance or mass to the moon as possible. That's inherent to the design. And we have made some improvements in the performance of the vehicle through what we found. We found mass savings in the vehicle where we could cut mass out, improved our flight techniques, and implemented propulsion system enhancements as well. Also, we are planning moving forward to preserve the capability for payload cryogenic loading at the pad. The second mobile launcher for Block 1B and Block 2 are currently in production, right now, and we already have that requirement set in there. And what this does is it allows you to load propellants within the fairing, and that work isn't 100% complete, but we're making strides to preserve the capability moving forward. And I should point out for BOLE, we are going through design analysis cycles, and we are currently passing requirements in Northrop Grumman. And I believe they're planning for a full-scale test, which is not too far down the road from here. Next slide, please. So baseline performance, if we were just to fly the vehicles as is, this is the C3 that you get. And let me describe what C3 is. It's essentially orbital energy. And what I show you here is how much energy you have after you're done burning your upper stage. And this is energy with respect to the Earth. So and if you are greater than 0, you're leaving the Earth-Moon system and you're going to heliocentric space or to an orbit around the sun, essentially. And the more energy you have above 0, the much faster you go with respect to, I guess, relatively to the Earth and the sun, if you will. So you're going much faster than the Earth if you were viewing the Earth and Earth-Sun system, Earth orbiting the sun. It's what's really amazing here is that we get fairly high performance out to high C3s that will take you directly to Jupiter. You don't have to do gravity assist. You can go straight to Jupiter, Saturn. But what's interesting here, we can do better. And I'd also like to point out the gray area down here. These are existing expendable launch vehicles. The upper bound here is shaped by the Falcon 9 Heavy. At least this is based on data that we have from LSP. And so these are very capable vehicles all around. And if you have a question about why there's a crossover here of Block 1 versus Block 1B, when you get out to high C3s, the stage mass becomes very important, and the exploration upper stage weighs a whole lot more than the ICPS. So that's why you see a crossover far out. So let's go on to the next slide, please. If you add up, so I want to talk about adding additional stages. So for this study, we chose a low risk engineering approach with using existing hardware. We use the Castor 30s, Centaur liquid upper stages, and then for third stages, and then for the 4 stages, we chose a Star 48 BV and GXV. Also, whenever we size our adapters that adapt these additional stages and the payload to the vehicle. I think we didn't size the payload adapters, but we did size the stage adapters. We use a heritage tool at Marshall Space Flight Center called LVA with it has 35 years of experience. It's fairly well validated, and we add plenty of margin on top of it to make sure that that design can actually be realized. Next slide, please. Okay, so these are the results of our study. How high could we get to C3 using additional upper stages? And what's amazing are these pictures on the left here. What you can't see is there's a spacecraft hidden at the very tip of that rocket. And this whole rocket is being dedicated to providing as much energy or as much velocity to that little piece of spacecraft at the very top. And it really starts at the gold piece and ends at the dish at the top, if you can squint and see it there. And these C3 curves are fairly high. It's not as remarkable at low C3, but it becomes very impressive at the high C3 range. So I'll draw your attention to the high C3 range on the right there. I have 3 areas highlighted. You can go about the Interstellar Probe mission 3 different ways, or at least that's what the study team devised. You could put as much energy into your trajectory as possible, and it's essentially consistent with what Michael showed you a little bit ago. And by doing that, you fly by Jupiter as best you can, get as much energy from that flyby, and you are going out of the solar system. And in his case, he showed a passive flyby of both Jupiter and Saturn, which gave a little bit more performance by the look of it. The second and third case here, you could actually just throw as much mass to Jupiter with a very large stage and do a powered flyby at Jupiter, which could give you high amounts of C3 as well. I would say maybe a 10% increase. And then the big and high risk option is a solar Oberth maneuver. If you were to go back and look at Herman Oberth's paper on this maneuver, it's essentially extremely ambitious. You have to do a flyby, a retrograde flyby of Jupiter, which arrests your motion with respect to the sun, and you virtually fall straight to the sun. And when you get there, you do a very large burn with a large motor, as large as you can afford, to give you delta V and get as much orbital energy as possible. I'll talk about that a little bit later. But these results were very impressive. The liquid stages performed very well. The red and pink grouping on top, for the third and fourth stages, and then for the blue grouping, those represent the solid third and fourth stage. And that also performed very well at very high C3. All right, next slide. Hello? Hello?
Hey there, Rob. We can hear you. I think that there's just a technical issue with on the James side.
Okay, thank you. I guess we'll wait.
I can take over and start sharing the slides from this point forward. If James has dropped out, I'll go ahead and do that.
I think I only have one slide more. And it's basically the conclusion chart, but this is the real groundbreaking result, as you can see here. It gives you far higher C3. And another thing to mention on this chart, you see New Horizons pointed. Oh, yeah, let's go back one slide just for a little bit. I want to point this out. This is what Michael was talking about. New Horizons, this diamond down below here, hidden underneath all these C3 curves, represents, well, at the time I produced this chart, the highest C3 that had ever used or ever flown, which was New Horizons. And now that record has been broken by Parker Solar Probe, but that gives you an idea of what C3s are talking about. We're able to achieve nearly double what was achieved for both of those missions. So next slide. And this gives you a little bit more insight into what C3 is. C3 is directly proportional to orbital energy. And the whole point of the Oberth effect that I was talking about earlier is that you do your burns very close to Earth. And this is just a representative set of trajectories for the vehicle. You can see how the core stage will burn, and then the exploration upper stage will burn and sit in low Earth orbit. and then it'll perform a second, the exploration upper stage will perform a second burn to go to deep space, after which the upper stages, the third and fourth stages, are burned, the Centaur and Star 48BB. So if I were to take advantage of the O-berth effect in this case, I would probably target the Centaur burn and try to put higher thrust engines on it. In this case, maybe a dual engine case to help shorten the length of that burn to get a little bit more performance relative to the O-berth effect. And essentially what it means is you want to be as deep in the gravity well as possible to perform that maneuver. All right. And that's, I think that's about it. This is just the wrap up. This is really America's rocket. This is produced all through the United States. Over 4,000 people work on this program with both government and on the contractor side. The manufacturing is complete for our first flight. We're getting ready to fly. And we have an evolvability flexible architecture that can enable things like an interstellar probe for achieving these really high outbound trajectories, outbound speeds. And we are excited about doing this kind of science moving forward. It's really an amazing mission. So with that, I'm done. Thank you for listening. And if you want to reach out to us, here's some links. You can reach out to us and talk to us about or ask questions about SLS. Thank you.
All right, and I think we have James back. If you want to take control again, James.
Yes, I am back. Thank you. Yeah, I'll share screens quickly.
And for all of you out there in the participant list, if you'd like to start asking some questions in the Q&A section, feel free. We have about another 15 minutes or so to answer any questions that you've got for myself or for Rob.
Any questions, anybody?
Glad to hear from you.
Relatively quiet crowd today. And that's okay. We have more to come in the months that are headed out. We have numerous webinars lined up and are going to be announcing speakers in the next few weeks as we go forward. And welcome any input here.
Oh, okay, great. We have a question. So it's from David Corin, and it's for you, Rob. So how much of the SLS production effort has been, quote, new design versus heritage? How will that impact future versions of SLS?
Well, we try to reuse what we could from shuttle to try to get our costs down for SLS. After all, it's a very large rocket, and a very large rocket is very costly, especially if you're starting to talk about especially when you're starting to talk about the overall infrastructure you need to build these items and to get to the launch pad. So we tried to reuse the cases of our boosters, which we are. We had to do some new things with them. We had to replace the insulation inside, and so it couldn't be used exactly as heritage. And also the thrust trace, how the motor actually burns internally had to be reshaped when we went to a 5-segment. So it's not exactly heritage like you'd expect. The most heritage item on the rocket is probably the RS-25. And that is actually one of the most expensive items on the SLS. And we are aware of the cost of the RS-25, and we have efforts in place to bring that cost down. In fact, I talked about using additive manufacturing on our new versions of our RS-25 that we're building right now. Potentially that will lower the cost about 33% with respect to that engine, but we're trying to keep that engine or preserve its design as best we can so that we don't invalidate all the testing that's been done in the past, if that makes sense. And that should help us moving forward through time as we evolve the vehicle. But
Thank you very much,
the heritage, go ahead.
Oh, I was going to say, you can please continue.
Oh, essentially, we use heritage to help lower our cost of development, is really the point, where we can.
Thanks, Rob.
Okay.
Yep, and we have some additional questions coming in now. So Michaela Dixon asks, can you explain again why you'd use a dual engine?
Yes, I don't know if you can go back to that slide on the C3. That'll be good. So I mentioned that the O-berth effect, sorry, one prior to that, go forward one slide. Keep going forward. There you go, this one. This explains C3, it has the equation written there. But the O-berth effect is essentially, you get more orbital energy. If you're performing a delta V, the upper stage is providing a change in velocity. It's accelerating your payload and the stage at the same time. If you can do the burn deeper in the gravity well, you get more orbital energy. So if you look at this Centaur burn here, which has a very long blue line, that is a very long burn. And as you progress through that burn, you get further and further away from the Earth, which is your gravity well. And so what would help you is if you could have more thrust, accelerate quicker, deeper in the gravity well, which would give you more orbital energy. Does that make sense?
Thanks, Rob. So yeah, we have a couple more questions coming in for you now. So Thomas Peave asks, the Falcon Heavy rocket already demonstrated flight in 2017 has similar thrust capabilities at an order of magnitude cheaper cost. How will the development of other commercial rockets shape the launch vehicle selection for the Interstellar Probe mission? And if Michael, you want to jump on that as well.
Yeah, and Rob might be able to add some more technically specific information in my answer, but the Falcon Heavy and the other commercial rockets that we expect to see in the near future that are coming to fruition, they do have high performance. They are heavy lifters, but they don't have the ability to lift 4 more rockets on top of them because of the mass that they can throw to those energies. And so they're definitely an add-in and a huge value to the overall space community. And we're really pleased to see them coming along. And actually, as a part of our study, we're looking at not just SLS, but if something should happen where there isn't an SLS vehicle available for us, what would our mission look like? How much slower would it go? How much less mass could we put into the spacecraft itself? And that's part of the overall assessment that we're doing with our study. But Rob, I know you know a lot more specifically about the performance of different launch vehicles, and perhaps you could explain the impact that the advertised performance of these commercial vehicles has on what the capability and the performance of the mission would be.
Yes, I'll be happy to. So the Falcon Heavy would have to be expendable. Right now, I think it's flown in a recoverable configuration for every single one of its flights. I believe the performance out to the moon is about 15 tons, or at least that's what SpaceX tells us. I'm involved in a lot of future mission planning as well, along with what I do with SLS. So I'm very much aware of what they can do. And right now they're quoting about 15 tons. And if you look at our Block 1 C3 curve, we're close to 30. So we're almost double. And then the big question is, well, what if I want to launch something big? The Falcon Heavy fairing is not a very big fairing. It's actually fairly tiny in comparison to what we want to plan to put out at the moon. So that becomes a limiting factor. And the SLS was actually originally built to be a 40-ton vehicle out to the moon that lifts very large monolithic structures. And I think maybe the Starship has a plan for that, but I haven't seen, I don't know exactly how that will shape up. It's not exactly clear at this point what their economic model will look like, how many times they have to refuel, whether or not it can be done. I don't know. And it's just something I can't speak to. But what I do know about the Falcon Heavy is its capability is much lower than what we are showing, in both delivered payload and its volume.
And the other aspect of this that is challenging to get my head around is yes, it's an order of magnitude cheaper for a Falcon Heavy, and orders of magnitude mean a lot in economic terms and in production terms. But when it comes to the energetics of rocketry, a factor of 2 is harder to achieve than a factor of 10 on the cost side. From a performance perspective, doubling the performance of a system like this is extremely challenging. And as Rob described, the difference between the Falcon Heavy and SLS with mass thrown to the moon, All those extra tons we need to put into propellant to send our very small spacecraft out as fast as we can. And that whole mass, velocity, and energy equation comes into play. And what we need is that velocity to get to the boundary of the solar system in about a decade. And that's the key here, is that the science team developing this mission and the scientists who will be a part of the formal mission, should it ever come to pass, and the team that continues it as it goes through the boundary and out into the interstellar medium itself. You know, some of them are in middle school now, even on the timeline that we're talking about. Some of them are in high school. Some of them are just beginning college right now, because it's such a long-term mission. And so without SLS, the timeline between now and when the science comes back just gets extended and extended and extended. And that's really one of the keys to the whole idea behind this pragmatic mission and what SLS can do for it.
And I'll mention one more thing. You know, I've said this to Michael several times, and that is, you know, SLS does get a lot of flack for cost, but I don't think cost numbers are truly ever understood with the SLS program. The more you fly, the overall cost per flight per year actually will drop. And the marginal cost of having one more flight for that a given year is much less than what you would expect. It's actually comparable to more of a Delta Heavy launch vehicle. So it's not as onerous as you might imagine.
Thank you very much, Michael and Rob. Our next question is from Drew Turner, and he asks, for Robert, can you please chat a bit more about the schedule for SLS for the Artemis program and how on schedule they are for meeting the needs for the Europa Clipper mission?
Sure, I'll be happy to. So COVID-19 has put a damper in things for us. I think it's impacted pretty much everyone's schedule across the board. We had to slow down our production at MAF, at Michoud Assembly Facility down in New Orleans. We had to virtually stop everything happening at our Stennis for Green Run. And that has pushed us out a little bit. We're now deeper into 2021 than we had wanted to be. And so Artemis 1 will be 2021. Artemis 2 will probably fall into 2023, possibly, depending on how quickly they can refurbish and how quickly we can get a core stage out of MAF. I believe we're planning on getting to about one vehicle per year when we get out to 2026 timeframe. 2024, I think we're going to have Artemis 3. So 2023, Artemis 2, Artemis 3, 2024. We may have a delay in reconfiguring everything for Block 1B. The problem when you get out to those years, it all comes down to the funding profiles for these immediate years that will directly influence what that will look like. So we are looking forward to it. And in terms of Europa Clipper mission, there is a gap currently in our manifest that could allow for Europa Clipper to fly. We are still working with Europa Clipper, the personnel down at JPL. We're providing them all they need in terms of analysis. And I think ultimately what it'll come down to is congressional support to push that through to get Europa Clipper flying in 2025.
Thank you very much, Rob. And so, yeah, the next question from Casey Lissy is similar to the last one. And so it's what are the upcoming real SLS launch schedule over the next 3 years? And maybe I'll add to this sort of other milestones that we should keep an eye on over the next 3 years as for how the program is progressing.
I'm sorry, could you repeat the question?
Sure. What are the upcoming real SLS launch schedule over the next 3 years? And furthermore on that, what are the milestones that we should be looking for over the next few years?
I would say getting to launch is going to be a big deal. I think that's when everyone's going to realize that SLS is real. And next year is what we're committed to. I would say we can really not fly later than July of next year. And that's based on the fact that we're stacking our boosters right now. There's a limit to how long we can keep those boosters still usable or in good shape, being exposed to the atmospheric conditions at KSC. You're right next to the ocean. It's not necessarily good air to be exposed to. So.
Okay. Thanks, Rob. I think we have time for maybe a couple more quick questions. So how many SLS B2s will be available to science missions through the mid-2030s?
It's a good question. And I wish we could produce, you know, 2 core stages or two vehicles a year and fly it that way, where we have an extra vehicle to use for whatever purpose may be needed, whether it's building additional architecture at the moon or going to Mars or even science missions. That's going to come down to congressional support, I believe, to make sure that we get the funding to be able to build these vehicles and make it happen.
Okay, thank you very much, Rob. And the next question, this will be our last question from David Gibson, and I'll let Michael address this, and if Rob wants to add a few comments, is how much plane change is desired for the Interstellar Probe to optimally test the solar bubble shape? I assume that would require just a Jovian encounter. What will that cost in a final velocity versus a Jovian and Saturn encounter?
Yeah, so all of our mission architectures fly by Jupiter. And so we will definitely be using Jupiter for a plane change. We haven't chosen a direction out of the solar system yet. In fact, the scientists working on this study are not in a position to say this mission must go in that direction or this direction. This year's study results will provide a trade space, if you will, of possible directions and the impact that it has on departure speed and science return and so forth. A future science definition team, should this mission go into the pipeline of one that NASA wants to execute, a future science definition team is the group of people that would decide what direction that is and why. And this actually speaks to the next question that Rosine has about whether it's going into the nose or to the side or into the tail of the heliosphere. So these things are all tied together. But I would say that the cost to the speed of going to Jupiter is a plus. Jupiter speeds us up. Leaving plane, not being flat in plane with the rest of the solar system will decrease the speed, and that is a pretty basic function of how high out of plane you want to go. And that's a trade that we'll have to make that the scientists will want to trade off in the future. Are we okay with taking a few extra years to get to the beginning of that turbulent boundary region if we go a few more degrees higher, a few more degrees higher, a few more degrees higher out of plane? What is the balance? What is the value of that? And that's not something that we're trying to determine as an absolute during this study, but merely to be able to characterize what the cost of those plane changes would be. Flying past Saturn, if we had a Jupiter-Saturn combination, would increase the speed a little bit because Saturn again gives you an extra gravity assist as you depart, and perhaps since it's so much less massive than Jupiter, it's not as large of a boost, and can also not take you out of plane quite as much as Jupiter can, and so that would all be part of the trade space that is considered down the road. And so these are all tightly coupled astrodynamics questions for sure.
Thank you very much, Michael. And that's all the time we have for today. So let me get to my, so thank you very much to our panelists, and thank you for attending today's webinar. The next webinar will be on Thursday, July 23rd at noon Eastern Time, titled Into the Unknown Local Interstellar Cloud, where we will have a panel presentation by Elena Pavornikova, Seth Redfield, and Rosine Lallement. Please visit the Interstellar Probe website for more information about the study and to view information on future webinars and events. Also, please consider signing up for our listserv under the community involvement section of the website to make sure that you are getting the latest information on upcoming webinars and events. Thank you for joining us and have a wonderful day.